Welcome to Ask and Learn.
We are given recurrence relations with initial conditions, and we are asked to solve. In part A, we're given the recurrence relation an equals 2an minus 1. For n greater than or equal to 1, and a0 is 3. We have that the characteristic equation is r squared minus 2r equals 0, or we have that r is equal to 0 or 2. So we have distinct roots, and therefore it follows that the solution is of the form an equals alpha 1, 0 to the n, plus alpha 2, 2 to the n, and substituting, we have that a0, which is 3, is equal to, let's see, this is going to be 0 plus alpha 2 times 1, and so we get that alpha 2 is equal to 3, and we have that it follows in general an is going to be 3 times 2 to the n. In part B, we are given the linear homogeneous recurrence relation an equals an minus 1 for n greater than or equal to 1 and a0 equals 2. This is actually easy to solve if we notice it's simply a sequence of 2's. However, to use a different method, we have the characteristic equation is r squared minus r equals 0, which has roots r equals 0 and r equals 1, which are distinct. And so it follows that the general form of the solution for this relation is an equals alpha 1 times 0 to the n plus alpha 2 times 1 to the n, which is really the same as alpha 2. And we have from our initial condition that 2, which is a0, is the same as alpha 2. So it follows that in general, solution is 2. In part C, we're given the recurrence relation an equals 5, an minus 1 minus 6, an minus 2. Where n is greater than or equal to 2, and we have the initial conditions a0 equals 1 and a1 equals 0. The characteristic equation for this linear homogeneous recurrence relation is r squared minus 5r plus 6 equals 0. And this can be factored as r minus 2 times r minus 3 equals 0, so that r is equal to 2 or 3. These values of r are distinct, So it follows that the general solution is an equals alpha 1 2 to the n plus alpha 2 3 to the n. And using our initial conditions, we have that 1, which is a naught, is equal to a1 times 1 plus a2 times 1. And we have that 0, which is a1, is 2 alpha 1 plus 3 alpha 2. And so if we subtract twice equation 1 from equation 2, we get negative 2 is equal to alpha 2. And we have that by back substitution, alpha 1 is 1 minus alpha 2, which is 1 minus negative 2, or 3. And so the general form is an equals 3 times 2 to the n minus 2 times 3 to the n. In part D, we are given the linear homogeneous recurrence relation an equals 4an minus 1 minus 4an minus 2. For n greater than or equal to 2, and we're given the initial conditions a0 equals 6 and a1 equals 8. The characteristic equation is r squared minus 4r plus 4 equals 0, which can be factored as r minus 2 squared equals 0. And so the characteristic roots are r equals 2 with a multiplicity of 2. And so it follows that the general solution is an equals alpha 1 times 2 to the n plus alpha 2 times n 2 to the n. And from our initial conditions, we have that 6, which is a0, this is equal to alpha 1, and 8, which is a1, is equal to 2 alpha 1 plus 2 alpha 2. And then using back substitution, we have that alpha 2 is 1/2 of 8 minus 2 times alpha 1, which was 6. So we get 1/2 of 8 minus 12 is 1/2 of negative 4 is negative 2. And so the specific solution is an equals 6 times 2 to the n plus negative 2, or minus 2n times 2 to the n. In part E, we're given the relation an equals negative 4 an minus 1 minus 4 an minus 2. Where n is greater than or equal to 2. And we have the initial conditions a0 equals 6 and a1 equals 1. characteristic equation is r squared plus 4r plus 4 equals 0, which can be factored as r plus 2 squared equals 0. And so the characteristic roots are simply r equals negative 2 with a multiplicity of 2. And so it follows that the general solution is an equals alpha 1 times negative 2 to the n plus alpha 2 times n times negative 2 to the n. And using our initial conditions, we have that 6, which is a0, is equal to alpha 1. And we have that 1, which is a1, is equal to negative 2 alpha 1, and then minus 2 alpha 2. And using back substitution, we have that alpha 2 is equal to negative 1/2 of 1 plus 2 times alpha 1, which was 6. This is negative 1/2 of 1 plus 12, or negative 13/2. And so the particular solution is an equals 6 times negative 2 to the n plus, or in this case, minus 13n over 2 times negative 2 to the n. I think a mistake was made in copying this problem from the book. So for part E, we should have that a0 is going to be 0. And so it follows that alpha 1 is going to be 0, and therefore that alpha 2 is going to be negative 1/2 times 1 plus 2 times 0, which is simply negative 1/2. And so the particular solution is an equals negative 1/2 times n times negative 2 to the n, which is going to be n times negative 2 to the n minus 1. In part F, we're given the recurrence relation an equals 4, an minus 2. For n greater than or equal to 2, and a0 equals 0, a1 equals 4. The characteristic equation is r squared minus 4 equals 0, and this has roots r equals plus or minus 2. These roots are distinct, so it follows that the general solution is alpha 1 2 to the n plus alpha 2 negative 2 to the n. And using our initial conditions, we have that 0, which is a0, is going to be alpha 1 plus alpha 2. And we have that 4, which is a1. This is 2 alpha 1 minus 2 alpha 2. And so adding twice the first equation to the second, we get 4 is equal to 4 alpha 1. So we have that alpha 1 is equal to 1. and therefore alpha 2 is equal to negative 1 by back substitution. And so we have the particular solution, an, is going to be 2 to the n minus negative 2 to the n. In part G, we're given the recurrence relation an equals 1/4 an minus 2. For n greater than or equal to 2, a0 equals 1 and a1 equals 0. The characteristic equation for this relation is r squared minus 1/4 equals 0. This has solutions r equals plus or minus 1/2. And so these characteristic roots are distinct, and it follows that the general solution is an equals alpha 1 1/2 to the n plus alpha 2 negative 1/2 to the n. And using our initial conditions, we have that 1, which is a0, is equal to alpha 1 plus alpha 2. And we have that 0, which is a1, is equal to alpha 1 over 2 minus alpha 2 over 2. So if we add half of the first equation to the second, we get that 1/2 is equal to alpha 1, and therefore by back substitution, alpha 2 is equal to 1/2. And so the particular solution is 1/2 times 1/2 to the n plus 1/2 times negative 1/2 to the n. And this can be written as 1/2 to the n plus 1. And here this is the same as plus 1/2 is minus negative 1/2. So minus negative 1/2 to the n plus 1.